Okay, more volume. On. Okay, lapel mic, that's the one. Hello? Hello? Aha. I think we've got volume. Good evening. My God, where have you all come from? I've not given a lecture to this many people in decades. Been away for a while. I'm amazed, absolutely amazed that in such numbers you're coming to data structures and algorithms. Last time I gave a lecture in data structures and algorithms, it was in Java, and it was 12, 13 years ago. So it's going to be a different experience this time. One thing I have kept is I'm using a wiki. Now, I'm not using the wiki the way you're supposed to use it. A wiki, programming wiki, is meant to share, and it means that people contribute. In theory, I should give all of you access to the wiki and allow you to make certain changes. And there will be moderation, of course, and the whole thing like Wikipedia. But I'm not going to do that. It'll just be standard lecture style, but I will try to get some kind of feedback loop in there, because errors can be fixed up. You have a view of the code and the statements that I make, which I don't see, and you would naturally, and if I have some good students who like to, well, I wouldn't call the word hack, but understand what I'm trying to say and say you've missed the point or you've made a mistake in the way you've said it, I can say it better. I'd like those to contribute. That way I'm talking at your level in a sense, rather than with my academic brain having done this for decades, and I have a way of thinking that I think you should think like, and that's not right. The one thing that data structures and algorithms has, and I will get onto that point later on, it's about thinking. It's not about doing as such. You're not laying bricks. It's not a standard mechanical process. You're not building a car by putting the pieces together in a certain way. You have to think about what you're doing and analyze what you're going to do and understand the consequences of what you're going to do. And that analysis and understanding is a human activity that you can't mechanize. It's the design process. That's the essence of computer science, the thought, the design, the algorithms and the data structures that have a marriage that together contribute to your programming. Okay, this is all a little bit too philosophical at the moment. Let's get into some nuts and bolts. I've got a lot of the 2018 stuff on the lecture slides here, and that's confused a lot of you. My fault. For example, when you look at the lectures, you'll see here week 2, week 3, programs, example in week 5, notes, graph reps, graph ADTs, and depth first search and breadth first search, and the programs. This is 2018. That course had reviews that almost shocked me. They were so good. I thought, my goodness gracious, how am I ever going to give a course with such difficulty I had when I gave this course in Java so many years ago, was the skill level was vast. I had students that could barely program, and I had seasoned software engineers who knew more about programming, certainly in the real world, than I did. And it's very, very hard to get the right level of course when you have people that really struggle from day one and others that find it boring until the last couple of weeks. And that you don't have that in undergrad. Undergrad it's just much more egalitarian. So but I'll be very interested with this number of people what skill level differences there will be, and that will come out in the first assignment and the quiz. And also the feedback I get from the two people that are supporting me in the course, Harrison and Kevin. Now, that's also new. Harrison is my course admin. I've never used a course admin before, but again, I've never had such a large course before. Using a course admin this year because to protect myself, not for the reason you're probably thinking. I spend a long time sometimes answering emails. A student asks me a simple little question and I'll give a 2-page answer, and I can spend many hours on that answer, thinking about all of the ways and all of the background, if you like, giving a lot of background to why I've got a particular solution. I've got to stop myself doing that with this number of students. So what I've decided to do this year for the first time is have a course admin who will filter. And as a student himself, a really high quality student, he will be able to, I think, understand better that you probably want a short, quick answer about something. You don't want a long tirade from me. So only when the problems become, what would you call it, more serious, and if they have to do with the administration, of course they will come back to me, or they will be filtered into me, towards me. So be prepared to talk a lot with Harrison, and we'll see how it goes. The other person, Kevin, will be doing the labs, and well, I won't say more about the labs just yet. That's otherwise I'll be going in front of talking too soon before I actually get to the course outline. Okay, so that's the basic administration of the course, or the management of the course. The three of us will be at your service in a sense. I won't talk about, I'd like to talk about the way we're assessing the course, but again that would be a bit too soon. Let's go in order here, otherwise I'm going to jump all over the place. Data structures and algorithms is about the marriage of the data structure and the algorithm. The last sentence there on the course summary is what's important. The content of this course forms the basis of a toolbox that every serious computer scientist, practitioner should have. Data type and structures, abstract data types, dynamic data structures, complexity analysis, and a whole bunch of tree and graph algorithms. That's when it really does get interesting, what you can do with string as well, string, tree and graph algorithms. By then, normally it was a couple of months down the track, but now it's 5 weeks in a 10-week session. I shudder at where some of you will have trouble getting your programming skills up enough in 5 weeks to get to the point where you can handle these algorithms, because they're very complex algorithms and the programming is just assumed. There will be a lot of address stuff, ADTs, a lot of pointers going around all over the place, data structures. They're very complex algorithms. And you must understand, you must know your programming. This is where we immediately have a problem. What can we assume? And the simple stuff, the fundamental data types, what's an integer, what's a character, arrays, what's memory, how to write and test programs, what's a procedural language, what's an imperative language, what's an OO language. I think all of you will know that, but I'm going to spend some time on that today. Know what linked lists, stacks and queues are, binary trees, and also be able to write a sort algorithm. Now, I've got a feeling we're making major assumptions here, because the last conversation I had with another lecturer who gave 9021 says no time, again this was Python, no time to do sorts properly, it's a terrible language to do it in, leave it to you. Oh my God, what's that all mean, and is it even true? Well, okay, so I can't assume this, and from that point of view, this is going to be a bit of an experiment here. I've got quite a lot of sorting stuff in my slides. I just don't know if there's enough time to do them. That's the worry I've got. Some really interesting stuff you can do with sorts, particularly quicksort. Quicksort, I think, was one of the real problem sorts from a Python point of view, from scripting languages, from these high-level languages. With C, you can do some really interesting stuff. But I don't know we'll have time for that. So what I can assume you've done is I'm not clear. So we'll have to see how it goes. The student outcomes are the standard set of scholarship and professionalism that you get from the lectures, from the assignments, from the homework, the problem sets, and from the examination, the usual things in computer science. Teaching strategy, again, we have the lectures, the problem sets, the assignments, and the midterm and, of course, final examination. Teaching rationale, the second paragraph is the most important here. Be mindful of the importance of spending time on actual programming. It is an investment. It will pay back in a major way as you progress in the course. The C language is particularly complex, requiring attention to both high-level and low-level. High-level abstraction and low-level detail. No abstraction. High-level, no detail. Pulling your problem apart into the high-level and the low-level is a major problem in the design of a C program. If you don't do it, you're going to have a mess, an unmarkable, unmaintainable, unreadable mess. C is ruthless or merciless from a design perspective. It doesn't help you. You have to do everything yourself. Most students require a whole session of practice at C programming to achieve the required level of competency. So I'll say right now, I'm going to say that again in probably a few minutes, is because of the importance of just doing it, even if you can't submit an assignment on time, even if you can't get it within the late time period, submit anyhow. If you can't submit without copying on time, don't submit. Take the time to do it on your own so that you learn from it. The learning is what is required for you to pass the course. The learning is essential, unless you're a C program already, of course. Now, the reason I say that, and the course is deliberately loaded, in a way, weighted, towards examination. You can't fake an examination. You can't copy in an examination. C will, I've seen students that are not very good with C get hung up in a 5-line program with the anxiety of an examination. Just simple, they get a pointer, one symbol that they've forgotten, program can't work, and they spend an hour trying to get it work in an examination situation. It's got to come naturally to you. If you make mistakes because you're not completely confident and know the how to program, you will come unstuck in an exam. In this course, 3/4 of the marks come from the mid-session and the final examination together. 1/4 comes from the assignments. Okay, you must not only pass the examination, you won't pass the course without it. Okay, so the examination you can't fake. There's no point really for you to copy from somebody else. I know there are a lot of issues with plagiarism in 9021 last year. I was following it. I tried to get Matthew to do this course as well. I thought a lot of you would be pleased to see him again. Unfortunately, he was involved in so many courses, it just would have overloaded him dreadfully. So we'll see how we go with the plagiarism checking, but there are no weekly assignment or homework or problem sets here. I'm not about to be a police agent. I'm not about to be the guy with the big stick pushing you to work every week to do something. You can do nothing, if you like, to week 4, and then hand the first assignment in. Then in week 5, do the quiz. Then you can do nothing to the end of year, end of session. Okay, so you have a couple of weeks in the middle of the week, in the middle of the session, and at the end you need to do something. For the rest of the time you have to do nothing. It's up to you. Postgraduates I'm not going to go after. So the problem sets will be there for you to exercise and to try to do when you have time, in a sense. If you don't do them every week, you will get behind. If you get behind, you're really going to struggle. Again, I'm assuming you haven't got these great C skills already. C is merciless in terms of detail. I have a lot of material on C, which is more, what would you call it, complex C, the details, the nasty side of C, rather than this is an assignment statement, this is a while loop, this is, none of that business is in my slides. I'm not here to teach you C. This is not a C programming course. This is where the regular dilemma of this course is, where do you position oneself? The positioning of this course is about data structures and algorithms. But you can't talk about data structures and algorithms without having a language. Just like you can't write a book without speaking the language, without communicating. What's a book without the language? You can't write a program without the language. The language frames the way you think. It frames how you represent data. So C has a very, very idiosyncratic, you could call it, way of representing data and in its expression of the algorithm. It's completely different to something like Perl or Python or even Java. So you need to get on top of the language. It has to come naturally to you before halfway, week 5. This is week 1. My problem with this tight timing is to give you a meaningful assignment. I consider it one assignment split in 2. The first half of the assignment is due before the first term, that first mid-session. So that's week 4, I've said. That means I have to give you enough material to be able to do that first assignment before week 4. There's no point giving you stuff in week 4 and expecting you to submit in week 4. So that's a major problem, and that's one of the reasons that I'm still moving a lot of my lecture slides around, thinking how I can rebunch it, regroup a lot of the slides so that they're more geared to what you need to do in terms of assessment. Okay, so there's an issue there. So you're going to get probably, not Thursday, but definitely by Monday, a part of the lecture will be devoted to a game that you're going to start programming in the assignment. But all that you do in this first assignment will be in a sense, the user interface, which is very simple until you get into the details, and then you realise there are some issues that need to be sorted out. And all programming issues, and almost have to apologise for that, but at least you get that stuff out of the road pretty quick, and then you can get into the more serious side, which is the real algorithm and the real data structure that you need to solve this particular puzzle. But that's all later on. So the lectures will be a bit strange at the start. Some of you may be bored. Some of you will find them too difficult. I've deliberately made the first lecture, which will be on Euclid, which I'm sure you've all heard of before. I'm very surprised if it's treated the way I've treated it. I hope not. Otherwise I've lost my originality, but we'll see. But it's meant to have you thinking. It's not a standard programming introduction. I'm not here to teach you C. I have to assume you know enough C to understand the programs I'm giving you, and I'll be giving you more C as we go along. It's a classic case, this course, of you learn by seeing the programs. That's why I've given you maybe 100, maybe 150 programs in this course. You'll see program after program after program. I don't like having program fragments. I prefer to put programs in their entirety so that you can actually see everything that's done from beginning to end, the whole program. So you can cut it, paste it, compile it, run it. 2 minutes. That's the basic building block of this course. The problem with that is when I write a program to put up there, you will, in some sense, it's not the copying that's the problem, but the way I have to program it to get it in the number of characters I've got, not too high, and not to waste things, time, programming space on ancillary or uninteresting things like input, output, error messages, all this stylistic stuff which a natural normal application would require the input to come from somewhere and require special formatting for the output. I haven't got time for that in a sense on a screen. I've got to put a program in a pretty condensed form together. But that doesn't mean I want you to adopt that as your style. Short and sweet is the way I program on the screen. You've got to take a much more humble, readable style, following the style guide of computer science and engineering from first year, mostly. But I'll get onto that in a little while, the style guide. Okay, let's get on to, I've gone ahead a bit far here. The conduct, respect to each other, and if you have any problem, there's a school ethics officer. Plagiarism doesn't play a big role from my point of view because 3/4 of the course is just going to be the first mid-session, or the mid-session and the final examination. The assignments is where we do plagiarism checking. Now the assignment is so, I wouldn't call it weird, but you're not going to be able to cut and paste from the web, no question. You may understand some of the things you need to do, but it's a very strange, not strange, it's an unusual assignment. It's taken quite a long time to put it together. Where the plagiarism will come, of course, is between each other. And that's what we'll be looking for when you copy from each other and you're using the same data structure, the same algorithm style. It's not going to be hard to find that because it is so much detail, it's hard to camouflage when you've taken it from somebody else. So I don't expect too many problems here because it's only the assignment where it's an issue and it's just going to be amongst yourselves where the copying is happening. Here again are the marks and the assessment. So there'll be just 10 marks for the first assignment. It doesn't amount to much, but it will give me a really good indication of how good your programming is. Then we have immediately after that's handed in will be the first examination. I'll make that as final-like as I can, just so that you get a good, get a first hit, if you like, at the final examination, first getting used to it. From memory, I have to have the final examination done by then or around then and submitted to UNSW. So I will be writing both examinations at the same time. So my thinking will very much be, okay, this is a practice question in the mid-session for the final. And if you can do this question, you should be able to do the final. That kind of thing. Okay, I haven't written that down anywhere, but it's natural for me to try to link the two a little bit. There won't be completely different styles of examinations, no way. Assignment then, after that, you can go to Hawaii for a few weeks if you like, and come back, and then you've got assignment 2, which is due, and the final examination. And if you find this course dead easy, and you know a lot of C, and you've done algorithms before, then maybe doing this work on the beach in Hawaii is not such a bad idea. You can certainly do it remotely on the website. Special consideration is something I've been talking to the school about recently. There's a hard line coming into the university about special consideration, and this hard line is called fit to sit. If you attend the examination, then you are committing yourself, and whatever happens on examination, you can't come back later and say, well, I wasn't feeling well, or these were issues that I had, I don't want that examination to count. So if you attend the examination, the result will stand. That's one thing, the fit for sit policy. That wasn't here just a few years ago. It's, for me, brand new. We were much more compassionate in earlier years. The other aspect of the special consideration, there are two other things I should say. Fit to sit is one. Two, don't ask for special consideration from us. I am not allowed to give it to you. And don't approach Harrison. It has to go through the student lifestyle department group. So they give special considerations. The third thing I should say is I have never believed in, and it's now becoming uniform, I understand, although I still question this, in giving supplementaries to those near 50%. So 47, 48, 49 has historically been, they're so close, give them a sup. Certainly academics I know have done it without hesitation. In fact, I know one academic who's incredibly popular, maybe this has something to do with it. If you fail, you get a sup. Full stop. You will get a second bite of the cherry, always. He says, well, if I'm writing the sup, I'll let everybody who wants to go for it again. So if you get 1%, you can have a sup. Okay, now, that's absolutely gone now. And even if you get 49 now, in theory, you're not entitled to anything. Okay, 49 stands. You consider yourself very unlucky, but it stands. So no sups unless you have basically a medical certificate. That's what it boils down to. Okay, so that's the special consideration stuff. Late submission, 1 day 80, 2 days 70, 3 days 60, 4 days 50, 5 days 0. I still believe, as nasty as that sounds, that it shouldn't be an issue whether you get 50% or 60% or 70%. It's scaled. This is, I scale your mark, whatever you got. It shouldn't be. The learning is absolutely essential. As long as you get some marks, you can still, by doing reasonable in the exam, well, every mark you get in an assignment is probably worth 2 in the exam. Put it this way, if you do it yourself. If you copy, there is no relationship between the assignment and the exam. The more you copy, the more likely it is that you're going to do a lot worse in the exam than the assignment. So it's a decision you need to make about how much work you put in. I mean, copy, that's not the only issue, of course. If you just don't do the work and you write something down which is rubbish, of course you've learnt nothing. You need to put in the effort. You cannot learn a language, natural or computing, without putting in the effort. When you have logic as well, and this weird syntax, addressing modes, the style of C, and this design problem issue as well, my goodness, there's some things you need to get used to. And that requires time. You've got to start almost from day one playing with the programs. Cut and paste my programs, change them, see what they do. The schedules is really up in the air. As I said, I don't know how to fill in a lot of things. I don't know whether I'm going to be doing sorting. I want to very much, but I don't know whether there'll be time. My thoughts at the moment, when you talk about tree algorithms, there are 2, 3, 4 trees, red-black trees, AVLs. These are weird structures, and maybe they're pushed a bit too much in this course traditionally. Maybe if you know one kind of tree and you understand the concept of balancing a tree, it's a data structure and a very sophisticated way of storing data. Maybe if you know one, that's enough. Maybe it would be better to spend then some time on quicksort rather than to learn that there are 3 or 4 ways of representing data in a tree. And then with graphs, it's even worse. It's a massive number of algorithms which you could learn. Maybe you don't need to know them all. Just one would be enough. So that's a decision I have yet to make about what to abandon and what to put in the course. Laboratory every week. I've set it from 4 to 6 on Monday, just so that it cushions up against the lecture. It has a disadvantage, of course, that if you want to stay longer, you would have liked to have had a 3 or 4 hour session in the lab. Then you have to decide, do I go to the lecture or not? What's more important to me, the lecture or continuing on in the lab? That's a decision you need to make, whether you think the material is good enough on the lecture slides that you don't need to, you're better off spending your time in the lab than coming to listen to me. It's a decision you need to make yourself. Kevin will be there, of course, for those 2 hours, 4 to 6 every week. If it turns out that these labs are really popular, actually you'd be making me really happy. If it turns out that 100 of you are fighting to get these lab positions and only 20 are coming to the lecture, you've really told me something with your feet. Okay? We'll get more labs for you. I'll get more tutors for you. If you're really that hungry to program and you can just read my lectures and know what's going on and say that's all I need to do, I don't have to hear him, then be my guest. It would actually make me proud. Okay? If all of you come to the lectures every week and none of you go to the lab at all, I don't think that's a sign of success. Probably means that you're struggling to understand what I'm even talking about and you need to hear it too, hoping that I'll tell you something that's not on the slides. Okay? And I want you to be behind that screen. That's what it's all about. Not there. Not sitting watching me, but behind the screen. I will be available for consultation every week. I've put that preceding the lab. So that means from 2 to 4, I'll have a consultation. From 4 to 6, there's a lab. 6 to 8, there's a lecture. It's all condensed and tight on Monday. Hoping, thinking that maybe some people will see that as an advantage of getting it all done on one day. Problem sets, again, are voluntary. Coming back to the 2018 stuff, which I've labelled. My apologies for not having done that sooner. I had all sorts of stuff from 2018, which some of it I won't be putting in the course at all and I'll be getting rid of, but I didn't want to get rid of it until I was sure it wasn't going to be useful, because what I want to offer you is as many problems as I can. Doesn't sound very nice when you put it that way, but that's what I want to do. I'm here to offer you problems. It's up to you whether you do them or not. I do have to make clear, of course, to you what is a minimum set of problems that you need to have looked at to be considered keeping up. And if you can't do these problems at least, you're in strife. And any more that you do is just going to make you better. Okay, there is a responsibility on my part to actually tell you what the minimum standard is. Finally, the text. I've used Sedgwick, I don't know how long, 10 years, more 15 years. I don't even open it anymore. I've used it so much in the sense everything has already come into my slides from Sedgwick, and I've had all this tutorial stuff and all sorts of things from him in the past. I haven't opened it for a while. I will be looking at it again just to make sure, to get some finer details, to make sure there's a certain match between what's in the book and my slides. I personally believe you can do an awful lot just from the code that I've provided you and the explanation I've given you, because I've come from a lot of places. It's come from a lot of places and a lot of experience. Sedgwick, however, is an excellent, excellent book. And you can see from the age of the book, it's been around for a while now, but this discipline has got a history, a very proud history, a very solid history, and Sedgwick really does put it together very well. So it really is a book that you can use as a reference. The first volume is the most important, parts 1 to 4 by far. The second is slightly more advanced. If you're going to just buy one, get one, second hand even, go for the first one for sure and leave the second for a little bit later. Particularly now with this 10-week business, it's putting pressure on the advanced stuff. Course evaluation, as I said right at the start, the student feedback from 18S2, not 19T1 or even 19T0. I haven't seen the feedback from those recent sessions. It's coming so fast, there hasn't been time to do all the processing. I'll probably be seeing that soon, and if there's anything interesting coming out, but with different lecturers using possibly different material, it's a little bit hard, and it's coming so thick and fast now, it's a bit hard to take the experience from the previous session onto a new session. It does happen at 18S2, which is Michael, who gave the course. He's first-class academic, first-class lecturer, first-class tutor, I would almost say. The material was very, very good, and that's another reason I haven't thrown it away, because my goodness, I thought they're nice slides. They're not programming enough for me, and I see a lot of code fragments. I prefer bigger picture stuff or more code. So that's what I've put into the course, and that's why I'm using the wiki. But you'll have to judge that for yourself. I'm not sure what I'll make available. I have a bit of a dilemma there. If I make it available, you'll think you need to learn it, and there may be stylistic differences in the way he does things, explains things, and uses different terminology, and then you may find yourself getting confused, and you find there's extra work when there's really no reason for it. I'm trying to help you, not hurt you, by giving you more material. So I'm a little bit careful about the lecture material. I've tried, so if it's interesting enough that I think you should look at it, then I'll put it into the lecture notes myself. That's the way I work. The problem's a bit different. With problems, of course, the problem's the problem, and it should be solvable whoever the lecturer was. So that's why the lecturing, the problem sets that he's had, I'll definitely be looking very closely at. But there are one or two I've already seen. I'm not sure where they're coming from, but they require you to think outside the box, very much so. I think, my goodness, it's not covered by the material anywhere that I've seen, the lecture material. Well, how can you do the problem? Well, that's the challenge. And I think, well, okay, in the first few weeks, I don't need that at this stage. I want to get you up to speed on the C, and then we'll see about the more challenging problems. He has a term for these challenge problems for those that want to do more. And I understand where he's coming from. I must admit, I'm not so interested in keeping the really bright ones interested in the course. So I've seen other academics spend a lot of time with the really bright students. Bright, maybe you should use the word experienced. They've done a lot of programming. My focus will absolutely be on the strugglers and the ones that are less than average. That's what interests me, and that means I will not have the time to get the high flyers flying even higher. Okay, they have their own reasons for doing the course, The strugglers are the ones where I get my enjoyment, my satisfaction, and that's the success of the courses. I consider how many people we get through. I've had courses where I've got 100% of people through. I've had courses, I had one course a couple of years ago. It was a programming course. I had one student in the front every week asking me questions. It got annoying, but I ignored that annoying part, answered the questions. He did the mid-session, barely passed. Came to see me right after, the day after. He, most unusually, didn't want any extra marks. He was only interested in how well he did, in how he should have done the problems, how he should have done the mid-session. We talked for hours. He left. It's the last I saw of him in the course. Until the next year. He was sitting in the front in another course that I was a guest speaker. I saw him and oh my goodness, I recognised him immediately sitting in the same spot. And I looked at him. Everybody was talking first 5 minutes. Noise, and I was getting set up and I was sort of half talking, thinking what I've got to do, and this is a guest lecture, and then he was sitting there and I thought, oh, how are you? And I kept working and he sort of was a bit quiet and he said, okay. And I said, oh, you're back in the same position. How did you do last year? This was my course. And he hesitated for a moment and I thought, oh, okay. But I kept working and he said, oh, okay. And then I wasn't thinking well. I asked him the question you shouldn't ask. What mark did you get? I just wasn't thinking. The moment I said that, with the microphone, everybody went quiet. And oh my God, what have I... And I really put him on the spot. He was really quiet. He was struggling the course, asking these rather simple questions every week. And then he's... All of a sudden, after a few seconds, he said 89. I should have seen my face. I couldn't believe it. 89. I said, you must be very proud of yourself. And I just went on to the lecture. I talked to him after. I said, what? How did you get such a high mark? And he said, that mid-session, the talk we had did me a lot of good. Something just lit up in my head. I sort of understood. And I studied and I hit the questions for the final paper bang on. He must have got close to 100% in the final paper. He said, I studied exactly the right questions. And it breezed through it. He was third or fourth in a class of 150 students. Okay, this was a struggling guy. So I'll never make that mistake again, aimlessly asking somebody how many marks they've got, possibly embarrassing him. But he was a real success story for me. If you work at it, you'll get there. He was a worker. And nothing fazed him. When I was answering his questions, that I could almost hear the second half of the course, he was asking me questions, and the others would get restless immediately when he opened his mouth. That is wrong. Interaction is extremely valuable, and I'll come back to it. I'd rather have 20 of you here and the rest of you on the screen doing something, if that's the best way you can learn the S&A. Okay, but the 20 should be here, be interactive. If you have a problem, speak up. Okay, that's the course outline. I'm not sure, I've got to open this stuff up. I assume no one can see any of this stuff, apart from the course outline. You can't see the lecture notes. True? Yeah, that's good. I just didn't know what you could and couldn't see. So I'm now in the wiki, view it in the browser, so this is what it's going to look like. The first bit of every wiki chapter, you could say, will be the little bit of an outline of the contents, and here you see the introduction to the course, and a bit of C, and what's software engineering, what's computer science, and then we get into Euclid and testing and timings in Unix. It's what would you call it? It's a bit of a, goes deep, sort of historical, but not. and it tries to give you, in some sense, a philosophy of what the course is about, an understanding of what we're trying to achieve in this course. Trying to separate out the language from the philosophy, the language from the thought processes that you need to have to be competent software engineers. Thought processes that are based in a language but are not governed by the language. They're there for communication purpose only. The language is there for communication only. So, teaching the aim of the course, to think as a computer scientist and to act as an engineer. And that makes computer science so strange and such a hard thing to define. It's completely different to a normal science in the sense that it is more disciplined to making, it's more a discipline to make something, what an engineer would do. But it's more than just engineering, it is fundamentally tied to logic, to mathematics. It is fundamentally tied to the processes of science. And you'll see that the birth of computer science was literally science, to bring structure and order into an activity. It's a scientific way of doing something. But it nevertheless is an engineering activity. So it tries to straddle the two worlds. And that makes it sometimes frustrating or sometimes more difficult than just building a bridge or being a biologist. You're actually constructing something which has to perform correctly. That's very much an engineering task, but it's got to be built on certain scientific principles. I'll explain more about that in the rest of this part of the lecture. The course used to be called Algorithms and Data Structures. No one's ever explained to me why the terms were reversed, by the way. Data structures and algorithms and data structures. I learnt it as algorithms and data structures. Here's a quote from Edgar Dijkstra. A programming language is a tool that has a profound influence on our thinking habits. I believe this is probably his most important statement, most important piece of philosophy. You'll see that Edgar Dijkstra was an outspoken academic from Eindhoven in Holland. He had a number of very confrontational, controversial moments in his life where he was very much against certain trends in computer science. And I'll show you what they are very shortly. It's hard to separate the language from the way we think. Obvious choice in when we solve a problem, the way we think about the problem, how we apply those thought processes to the data structures and to the algorithm will influence the portability, the maintainability, extendability, scalability of that product. C is nasty in that you have to program multi-layered. C gives you nothing free of charge. You write your own libraries, basically. Of course there are C libraries. But generally, if you're doing something in C, you want to tailor-make the data to your particular problem. So libraries are not used that much. No, packages are in some sense foreign to C people. C++ is different. C++, there's a whole different world of C++. C people tend to write everything themselves from the ground up. The concept of an abstract data type is in some sense foreign to C. It's just not a natural language to express an abstract data type. But it is absolutely imperative that you do use them, because without it you have a monolithic piece of code which is unmaintainable. And after a week, you will forget yourself how it works. So abstract data types I will introduce as quickly as I possibly can because they're just so important to structuring your program to separate the high from the low level. Here's a picture of Edgar, died in 2002. His period of extreme productivity was in the 1970s, late 60s, early 2070s. He was awarded the what was he awarded? The Turing Prize in 1972. He was a physicist originally. In those days there was no computer science. I also did physics in those days. A lot of the computer scientists of those days were mathematicians and physicists. There was no computer science degree as such in the 70s. They were all mathematicians and physicists. He developed a new programming style based on science, and he was the first one to do that. And one of the reasons that he decided that it was not required was a conference in 1968 in America, run by NASA. And NASA, these are the spin-offs you get with high-tech things, brand new challenges for mankind. One of the spin-offs was NASA had a lot of software, needed a lot of software for their spacecraft. Everything was electronic, everything was programmed. And they found the programming was abysmal, the quality, the bugs were everywhere. It was chaos, it was a circus. So in 1968, some of you people here probably, your parents weren't even born in 1968. Maybe that's a bit of a stretch. In 1968, they signalled and coined the term software crisis. And that was about the time that Tony Hall and Edgar Dijkstra were doing their big work. And they were putting formal rigour into the act of programming and analysing programs for correctness, verifying the correctness of programs. That's why he was awarded the Turing Award in 1972, and companies like NASA realised the incredible importance for mission-critical systems of having well-designed, well-written programs. There's no point ad hoc writing a program and trying to do something with it if it's life-threatening. The great mathematician, Dr. Knuth, he was the Sedgwick of my day. I don't know how many volumes, 6 volumes. He was a mathematician, everything was highly mathematical. He was the god of computer science in those days. And he wrote, "A revolution is taking place. We are beginning to understand the associated mental processes more deeply. It is impossible to read the recent book Structured Programming by Dijkstra, Dahl and Hall without it changing your life." Now, that term, structured programming, came from Dijkstra. He's come up with, as I said before, controversial statements, one of which is computer science is no more about computers than astronomy is about telescopes. I disagree with that to a degree, to a certain extent. It's true, but not true. And it's certainly not true when you talk about C. A C is all about the memory, the cache, stacks, you name it, it's in there. Operating system, it is about the computer. So the reality is you can talk about writing algorithms and analysing the algorithms separate from the computer, but it's not practical. If you apply it into the real world, you must include the computer in your analysis because it makes all the difference. You analyse something that's written in Python, it's going to have completely different performance if you did it in C. You must take into account the computer that's underneath it. The use of COBOL. I'm not sure how many of you would know COBOL. It dates you immediately, because, well, maybe there's still quite a lot of COBOL about. It used to be the most common language on the planet Earth. It was used, there are millions and millions and millions and millions of lines of COBOL in circulation being used by countless thousands of companies. It was the use of COBOL cripples the mind. Its teaching should therefore be considered as a criminal offence. I have a lot of sympathy. When I first saw that statement from him, such a long time ago, I was immediately, he became my friend. The one course I almost failed in computer science, when I did that eventually, was COBOL. I hated it. I didn't understand it, I didn't like it, and I did badly at it. So when I read that from Dijkstra, I thought, well, maybe there was some underlying reason why I disliked the language so intensely. But there are people who believe in it fervently and think that this is the perfect language for the business world. It's a business world language, very verbose. Okay, that's COBOL. Simplicity is a great virtue, but it requires hard work to achieve and education to appreciate. And to make matters worse, complexity sells better. That is a really insightful statement. Complexity sells better. People like things to be really complex. One of the things that will come out of assignment 2, which can get complex if you don't think clearly, is, how would I say, the marks. I like giving marks for people that solve problems in as few lines of code as possible. Somehow there's an elegance and a sweetness when it's short and does the job and can't, but nevertheless be robust, can't fall over easily. You don't want to make it minimalistic code that can only take one kind of input and after that it'll crash. Talking about robust programs, but simplicity is the key. So for goodness sake, don't get into this mindset where the more lines you produce or throw at me, the more marks you can get. There's somewhere there are going to be some good lines in there, and you'll pass. At some point, and this will be part of the marking, and I will tell you when I give you the assignment, that there's an efficiency consideration. If you solve problems correctly, but with bad code, if I could call that, with extra code, with verbose code, you will lose marks for verbosity. Not because it's wrong, because it's bad style. It's just too verbose. Okay, don't think that more is better. Absolutely not true in programming. Certainly the assignments that I had in the other course, which is a programming-based course as well, the students that get almost 100% are the ones that almost have the shortest solutions. There's this elegance and simplicity that I really appreciate. Another quote from Dijkstra, which you'll hear from a lot of academics, that testing is used to show bugs but can never show correctness. You'll never know with testing that a program works 100% of the time. You can only show that a program has a bug if it fails. You can prove nothing with testing. Zero. Proof and testing are two terms that you can't use in the same sentence, in a sense. Okay, it's not a way to verify correctness. Testing is a way to show the program doesn't fail for certain input. That's all it does. Okay, you have to understand the limits of testing. I'll come back to that in a moment. Another quote, object-oriented programming is an exceptionally bad idea which could have only originated in California. This created a lot of controversy when he said that. People in California were not happy. Okay, but this quote has had a long life. A lot of people have analysed it and said why it's true, and there are people, of course, that disagree. Now, why did he say this? Well, you have to understand who Dijkstra was and what he tried to achieve. And what he simply tried to do in his what would you call it, his study of structured programming, term structured programming, was to prove code correct. If you couldn't prove it correct, you had to assume that it wasn't correct. You must be able to prove code correct, otherwise you shouldn't use it. He was a disciplined person. It had to be correct. If I can't prove it correct, what's it worth? So that's where he was coming from, and OO causes major problems in terms of proof of correctness. You cannot apply his colleague Hoare, Tony Hoare, great mathematician, much more a fundamental guy. Hoare's calculus was used in the other course that I give in the next session. In fact, I use Hoare's calculus to prove C-like programs are guaranteed correct. No testing. Only through calculus can I prove, all I need is calculus, Hoare's calculus, to prove that a program is 100% correct. Of course, I have to take out certain C primitives, which you can't use, you can't have pointers. It sort of limits you immensely. And what you absolutely can't use, because it's a C-like language, are object-oriented concepts like inheritance and polymorphism. That's crazy stuff, which I should get onto. So, what's the problem with OO, and why does it cause a problem for analysis, for proving correctness? Well, OO is suited to business-like applications. Speed is important to market, and the correctness is less important. If you happen to put something in the market that doesn't work 100% of the time, okay, people today, more so than years ago, people would wear it, just accept it as it is. Today, of course, there are more demands placed on manufacturers to produce quality products, but in those days, it was more accepted. Okay, it wasn't going to be perfect, but that's what you bought. Testing is all you need for this so-called correctness. If it worked for the general context that a particular product had to work in, that was enough. It didn't have to be robust and be adaptable to other contexts. That wasn't required. So the answer is no. The features that OO give you of polymorphism, different typing, dynamic typing, and inheritance, types and subtypes, are things that are extremely useful to develop code quickly. They defy mathematical analysis. Another view, the OO paradigm, you can see is a layer on top of an imperative paradigm. Imperative basically means action, data, action on data, new step, data, more action, data, more action, data. It's imperative. Verification can prove that layer, which is imperative, correct. The moment you put OO on top of that, you've lost correctness. It can no longer guarantee anything. It can only guarantee subsystems of structured code. A more cynical view is if you take a structured program that you can mathematically model and prove correct, that's one layer. You can then on top of that add go-to statements. These go-to statements allow you to unstructure your program. The result is a mess and unanalyzable, unprovably correct. It's just too complex for a mathematician to prove correct. It becomes spaghetti code. Well known to you all, I'm sure. Now, we haven't even touched OO. Now, OO is another level, and finishing that off, it was Dijkstra's quote, in fact, way back in '68, the go-to statement as it stands is just too primitive. It is too much an invitation to make a mess of one's program. It wasn't a bad thing as such. He wasn't so against it, but it just open slather then in your program. You can make a hash of your program logic and you would not be able to prove anything about the performance or the correctability. Where does OO fit in? Well, after you've got the structured level where you can prove correctness, and you've got the unstructured go-tos coming in there, continuation statements and break statements and all this stuff, which allow you to zip all over the place, that's spaghetti code. Then you've got the OO level. And this added complexity is not statically analysable at all. It's completely dynamic. All of this polymorphism is happening at runtime. What can you do statically? You don't know what's going to happen. How can you analyse anything when you don't know what's going to happen? It's just unpredictable. So they say it's spaghetti behaviour. So it's worse than go-to programming, which is spaghetti code. It's spaghetti behaviour, and there's no way you can analyse it. So that's why a lot of formal method people write off OO, as when you do OO, all bets are off, they won't support you. If it works, it works. If it doesn't work, goodness knows how you're going to find out where the problem lies and whether it's a design problem or what kind of problem it is and how you're going to debug it. You're in trouble. Okay, but it's fast. Programmers have a lot of things that they're available, all sorts of libraries, this wonderful idea of information hiding from OO. But it's necessary, because if you didn't have that, my goodness, you would have problems. Then you'd really have a mix of go-to programming and this chaotic structure on top, dynamically speaking. So the advantage is speed with OO. Correctability goes out the window. Now, I might go through this pretty quickly, the software engineering and programming. The difference in essence between a programmer, and really in the software engineering courses that I give come down on this concept of a programmer. Programmer is what I consider to be a slave, somebody who just does a job on his own or her own that fulfills some kind of requirement. A software engineer is somebody who works in a team who must design an algorithm data structure pair to solve a set of requirements. And that's a much more complex task than just programming a solution. Unfortunately, with 400 of you, you'll all be treated as programmers and you must work on your own to solve a problem. And what we try to instill in you is the idea that you're an engineer, that you're actually presenting or submitting a piece of code that has to fit into an environment, into other code. It has to satisfy a certain specification. That's what a software engineer does, satisfies specifications, which are the embodiment of requirements, if you like. That is a team discipline, a team thing, which makes him or her an engineer. It's not a sole activity like reading a book, writing a program, solving a puzzle, hacking on the computer. These are much simpler tasks. Classical engineering, I'll go straight on to, I think, what's most interesting here, the difference between classical engineering and software engineering. With classical engineering, you're building a bridge, or you're building a train, or a car, or a bicycle. You're building a tangible thing that has to perform. There are two phases. You design the thing, think about it, work out what it's going to look like, and then you finish your design and you build it. You don't say halfway in building a bridge, oh my goodness, I think we'll put another lane on that bridge. I think we want a second train line to go north-south instead of south-north kind of thing, two directions. You can't do that. You have to have designed the bridge completely, and then you start building it, and there's an absolute point between the two. Software is different. Software, one, there's no tangible thing, and two, the design process actually almost never stops. Programs that are written, are maintained, are extended, are changed. The requirements can change well after they've been sold or well after they've been distributed to the customers. The customer being the companies that purchase them. So Facebook and all these companies that buy software, appropriate software from other companies, they have certain requirements. When they get the software, this software develops, evolves, changes. It's an ongoing process. So there's no starting time for the manufacturing process. It's a continual change, evolution in the requirements. In some sense, the irony is there is a time when it's no longer worked on, the software. It's then called legacy code, which the reason that it becomes legacy, in a sense, is dead. From a manufacturing point of view, that's when something will be manufactured. From a software point of view, it's the time that it can only be used and no longer developed, for the reason that the people who understood it have gone, moved on to other things. There's nobody left who understands enough of it to maintain it, so nobody touches it. And it just becomes, what would you call it, an anchor that holds you back because you can't change it. It's dead, but it's still essential for some kind of activity, some kind of process for a company. So it's a completely different world, software engineering, to classical engineering. But they're both engineering. More than that, and this is the analogy I often use, when you build a bridge, we'll come back to testing again, you can test that bridge pretty well. You say this bridge has got to take a few thousand tons before it collapses. You put 2 trains on that bridge, you can be sure anything less than 2 trains of weight, that bridge is going to stand. There's no way I'm going to walk over that bridge and it's going to collapse because it couldn't handle my weight, but 2 trains were okay. That's physics for you. No problem here. It's straightforward, predictable. Try that with software. You have just one parameter n, one input variable. You're not going to say, you cannot say, well, it works for n equals 10, so it's going to work for anything less than n equals 10. It's a ridiculous concept. Or anything more than n equals 10. It could fail with n equals 11. You don't know if n equals 11 causes the denominator to be 0 somewhere. It'll crash. Segmentation violation. End of story. You can't predict that. So you're going to have to try n equals 11 and 12 and 13. Maybe a million will make it crash. Maybe a big number will make it crash. Maybe a negative number will make it crash. Anything can make it crash. How are you ever going to know it's going to work? You've got no law of physics. There's no gravity here. There's nothing that says that if it works for something, it's going to work for a lot of other things. Well, there is. And that's mathematics. So if you can prove inductively, through the logic in your program, through the statements that you've got, that this loop, set of loops, will produce correct behaviour for n equals 1. And the step from n to n plus 1 is guaranteed to be correct, then you know that for all n, that program is correct. That is verification in a nutshell. If you understand that, you understand verification. If you can logically argue, mathematically argue, that your program construction, program design, is provably correct for a particular base case, and for every increment, then you have proved correctness, and you're using the laws of mathematics to say this program is correct. Just as, in a sense, you would prove that a bridge is not going to fall down for particular forces by proving that for a particular force it's okay, therefore anything less it's going to work okay. Physics is working for you. Okay, so discrete worlds, the discrete world of programming, where zeros and ones, true and false, on and off in a sense, are all that you've got. There they don't support you from a verification point of view. You must use mathematics to prove correctness. And that is why it's so important in mission critical situations, or economically critical as well, when you're talking about millions of products, that you use structured programming, that you can prove correct for all situations. You can't do that with OO. Okay, so definition of electrical engineering, or software engineering from the electronics engineers, IEEE. What is computer science? Oops, that's going too fast. What is computer science? This is interesting because now, in a sense, I've pushed the engineering side. When you're actually trying to build something, be an engineer, think of and analyze the design and prove the correctness of the product. As an engineer would do it. If you build a bridge, it must work. You must test that it works, because unlike an operating system, take Microsoft Windows, that is not designed to last 1,000 years, 100 years, a year, even a month. You don't have a reset button on the bridge. It comes crashing down, you don't say reset, and up she comes. You do that with an operating system, some of you will be hitting the reset button every day. You don't think twice about it. You're perfectly happy to accept a system, complex system, that falls down, because you know how to get back up again. Nobody loses their life. Well, that could happen under certain circumstances, of course, in transporting aircraft, in medical world. These devices become critical, the performance, and they have to be proved correct. And you cannot do that by testing alone, as I've already mentioned. So, that's the engineering side. The science side is more fascinating in a way, because if you think about it, I'll give you an assignment problem, and then you have to think of the algorithm to solve the problem with the data structures. You write your program, and then you execute it, and there'll be computer processes. Now, what a scientist does, and maybe you've never thought about it, is that they classify things. They order the world and try to understand how it all hangs together, and they classify it in biology, for example. You classify animals in species, in groups with certain characteristics, and all of the animals that have these characteristics belong to one family, and there's another family and other families. So that is the order that science brings, and you have an analysis, if you like, what the relationships are between the different, and whether there's a hierarchy, if you like, in certain characteristics. That's what scientists do. They don't even think twice about it. That is in their DNA. In computer science, we do the same thing. We classify problems. We try to work out which problems are a family requiring the same solution. And generally, put it in a very simple way, this analysis is based on complexity. So we have the linear problems, if you like, and the quadratic problems, when the performance goes like the square of the input. And then you can eventually get to exponential, and even worse, exponential of exponential. So we classify them in terms of difficulty, of complexity. But it's a very confused world in a way, because you have to associate, you have to link the analysis of complexity to the underlying computer. That's why that statement that computer science has nothing to do with computers, because it's the same relationship as astronomy is to telescopes, is wrong. The analysis of complexity inherently requires you to understand what the underlying machinery is. And for example, the same algorithm expressed recursively or expressed iteratively can give you a completely different performance, which puts it in a completely different family. So the basic structure, underlying structure of the computer that you're dealing with is essential to understand the complexity and hence the speed. Okay, let's get on to something a little bit more interesting, something a bit more concrete. Understanding or knowing how fast a program is for a piece of data is in some sense useless. It doesn't tell you anything. You need to understand the behaviour of a program over a whole series of data. And then you can understand what the, if you like, degradation, what the performance loss is with increased size. So, we classify algorithms by how the speed changes between different sized inputs. Take, for example, Euclid's algorithm, and that is a so-called smart algorithm. If you have two inputs, x and y, where for simplicity's sake we'll always assume the second number, y, is the least of the two. GCD of x and y, using the algorithm from Euclid, is, well, if the smaller number is 0, the x is the greatest common divisor. If it's not 0, then you move the y to the x and you replace the y by the remainder of x divided by y. That's Euclid's algorithm in a nutshell. So I've expressed it here as simply as possible. Y equals 0, then GCD x and 0 is x, so we're finished. It's the end of the recursion. Otherwise, we recurse by replacing the x by the y. The y moves here, and this is the remainder, x mod y. So you, in fact, Euclid, when he first, I think it was 2,500 years ago, something like that, when he did this algorithm, he didn't know about division, they didn't have that. He talked about subtraction. You take y off that x, keep taking y off the x until you can't take any more off. Didn't know about negative numbers either. And when you've got a smaller number than that number y left over, because you can't take it off anymore, then you're finished that operation, x mod y. Okay, and then you apply the GCD algorithm again and see if that's 0. If it's 0, you're finished. If it's not 0, you do it again, and you do it again, and you do it again till it is finished, 0. There's 56 and 21, 56, 21, 21, y goes to x, 56 mod 21 is 14, 21 and 14, y goes to x, 21 mod 14, the remainder is 7, 7 goes to the x position, the remainder is 0, 7 divides 14. Okay, so we finished with 7, GCD of 21 and 14, 56 and 21, or 21 and 14 is 7. This is Euclid's algorithm. It's the oldest known algorithm to appear in print. What was it? 300 BC, 300 plus 2019 years ago. It's actually an algorithm based on subtraction. To quote from Euclid himself, whoops, wrong button. We'll go away. What have I done? You've got to think about this. I mean, I don't know how much is translated, whether it's from Latin or Greek. No idea. When two unequal numbers are set out and the less of the two numbers is continually subtracted in turn from the greater, if the number which is left never measures the one before it until a unit is left, then the original numbers are relatively prime. Wow. I mean, the English is pretty horrible. We don't know if the Greek or the Latin was pretty horrible too, and who understood it in those long times ago? That's such a long time ago. So, okay, there's Euclid with his algorithm. What's this in C? Here's your first C program. It's good that it's Euclid. At least we're starting this course really on first principles. We're starting it with basically the first program that was written 2,300 years ago. Now, we've got a lot of ground to cover from 2,300 years ago to the present day. So there'll be a lot of programs. Okay, here's our little program. Again, it's an educational thing. It's not necessarily what I would use if I was going to send a robot to Mars, and that's not allowed to crash, so it's not mission critical. I've got a couple of include statements at the top. Don't know if you know what an include statement is. It's a recursive program, and I have two numbers, big numbers. Don't know how many digits now, 3, 6, 9, 10, 11 digits, looks like. If y equals 0, return x. That's what I just had. Otherwise, I put the y into the x, and I do the remainder, the x percent, which is the mod operation in C. So you've seen a few things happening here. Here's a C program, and I'm calculating the remainder here, and I'm calling Euclid again, it's recursive, and I'm passing the y as the x into the next version. This should not be hard for you. But it's sophisticated programming. It's not a simple little loop, it's recursion. Program 1, recursion. Program 1, 2,300-year-old algorithm, the start of, you could say, computer science. Well, a lot of people would say that's a bit too soon. Okay. Now, what can we note here? It uses long. Oh my goodness, here's our telescope. I didn't want to know about this, but I do have to know. Long? What's long? What's short? What's middle? What's anything here? This is a computer. I need to know what I'm working with. Otherwise I won't know what I'm doing. And this is where C is merciless. You have to understand the architecture. C doesn't beg you to understand it. It demands you understand the architecture. What you see is not necessarily what you get. It'll do weird things if you don't know what you're doing. So, the long, which are 8 bytes instead of int, just 4 bytes. So that's where the definition of long Euclid, you think, what's long Euclid? Why isn't it short? It's a long number. It's a double int. Means you've got more bits. Do constants are hard-coded in this program. That's ugly. If you do that, I'll fail you in the course. These are magic numbers. One thing that first year will teach you, some of you may not have done first year here, never use magic numbers. A magic number is a number that comes out of thin air, just like a rabbit out of a hat. Where do those numbers come from? Well, I've got to do that for the sake of the lecture. I can't here have a dozen lines saying type in a number. It wouldn't be any point. I'd have to work my computer. I would do it on the computer. You would go home and say it all flashed past me. Okay, so simplicity is, I give you the numbers here in the program, hard-coded magic numbers, which is bad from a programming point of view. So I try to say that don't do it, but I have to, because this is education. I'm not sending something to the moon. So you should use hash defines. It's simple, just put the hash define in, put the numbers in a hash define right up the top of the program, so you've given it a name which is meaningful, and somebody can maintain it if you want to change a number. They can easily replace it. So the x% y is modulus. Compiling the program. Here, I'm using DCC. A lot of you will never have heard of DCC, I would assume. Maybe you have, maybe you haven't. I hadn't before recently. I've been using GCC for many years. But DCC is now the compiler, the C compiler. I don't even know what D stands for. GCC is the GNU C compiler. I've known that for decades. DCC is much better. I'll get on to more of this analysis of what is DCC and what is GCC. The two different compilers are basically two compilers. DCC is actually a compiler called Clang, C language, Clang, typical C kind of name. Clang is a compiler, and it's got all sorts of things around it to give you better error messages. So they really push it in first year for consistency, that everybody has the same kind of compiler, same quality compiler. It's better and more forgiving than GCC. But that's by the way. So it's DCC, Euclid, and it'll generate an A.out, an executable program, which you can run. I presume I run it. Here, I give you prompt. This is as if I was on the screen. I run it here, and it comes with those two numbers, 1. Okay, what's 1? The GCD. In other words, they are mutually prime. Okay, there's no common factor. Okay, all right, you can believe that. That little program says there's no common factor between those numbers. I don't know if any of you are thinking as quickly as you can to see if you can find out a factor. Looks like 3 might go in there. Maybe quickly I could try a 3. If 3 doesn't, what do I try? 5 won't, and 0 won't for sure. It's not even, so it's not 2. 11 maybe? Not looking good. So maybe it's believable that there are no common factors. It's a pretty good bet if I gave you that question. And absolutely I will not, of course, 2 wildly long numbers and say, what's the common factor? Well, I think I know what you're going to do. By necessity. Well, we'll see how it goes. Now, there are a couple of other little things here. I've got a print statement in here, printf. Now, the includes I'll mention very quickly, just in case you don't know. Why are those 2 includes up the top there? They're header files. I've got one standard IO, std.io, that IO, and IO does the print. Boom, 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 printf. And it's got a %LD, L long distance, long decimal, LD, long decimal, prints in decimal. So that's what that's all about. And it also returns exit success. Classic first year programming. You must return to the operating system that calls you whether success or failure. And exit success is defined in standard lib, stdlib.h. So basically every single program you write from now on, you don't even think about doing anything different. In fact, you should still have your eyes closed when you're sort of, what am I going to do? Write down standard IO, standard lib. 2 lines immediately. Every single program you write will use them. Okay, it's so easy. Programming can be somewhat mechanical. And you can, if you like, write int main, maybe void, and you can write return exit success as well. Now you've just got to fill in the middle bit. And the middle bit here is the print which calls Euclid, who is audible 2 numbers. Okay, so the recursion is happening in the print statement. It's not really pretty, but it's certainly short. Okay, so there's our program. Return to mains page. Now, I can test that, but also I can, of course, say I don't believe Euclid was right. What could he possibly have known 2,300 years ago? The guy was a barbarian. I'm just going to do it the brute force way. I'm just going to start with, now I've got 2 numbers. Consider each number from 1 to x, say. If it is a factor of x and a factor of y, then the solution is going to be, its solution is the greater such number. Okay, you want the biggest number that divides into x and divides into y. It's the greater of the numbers that do that. So you want that property. Now, this is exhaustive search. I exhaust all possibilities till I get very tired, and eventually I'll get the right solution. But I'll be very tired because it's going to take a long time. You can sort of feel that coming. When I show you an 18-digit number, there are a lot of trillions in there, and so you're going to have an awful long, big loop. Now, the first thing that you've obviously said, every single one of you should think, well, if I've got 2 numbers x and y, they're not the same, so one is smaller. The greatest common divisor is not going to be bigger than the smaller one. Is everybody happy with that? If you're not happy with that, I'd prefer you withdraw from the course. Okay, the common divisor of x and y is not going to be bigger than the smallest of x and y. Please accept that. Understand that. That's really important. Okay, so we never have to go to the smallest, we never have to go past the smallest of the 2. Now that subtle, obvious thing is amazingly powerful. You'll see that come back a couple of times. That obvious thing that the smallest of the 2 numbers determines something here in terms of performance. But okay, so the first thing I would say is this algorithm should only go as far as the smallest of the 2 numbers. But okay, there's an algorithm there. I've got 2 algorithms. I've got the brute force exhaustion technique, and I've got Euclid's 2,500-year-old recursion. Let's test them, but we'll handicap them. Don't trust Euclid. I'll give him a little old calculator from the 1960s that does 1 Hertz computer. So basically it does an instruction every second. Instruction every second. 1 Hertz. I don't know if they've ever been that slow, but okay, this is this imaginary machine that is so slow, it's every second it does 1 instruction. Really slow. And then I'll take a modern computer, does a couple of billion every second. So 2 billion times faster, use exhaustion. That way I know when I get the right solution is absolutely right, because I've tried every other solution too. This one's definitely the only one that works. None of this pluck it out of the air using a couple of steps in recursion and pray that it works, or it's the best one. And I've got some execution time for you to actually show you what happens. Okay, Euclid on a super slow machine, and exhaustion on a blindingly fast machine. And you can see with 121 and 55 the GCD is 11. Not too hard to think that's true. It takes 1 second using Euclid on this slow machine. It's basically, because 55 and 121, they have a GCD, it's basically just 1 iteration, 1 recursion, it's actually 2. And on this exhaustive machine, it takes it 1,000th of a second, so it's 1,000 times faster. But when the numbers get bigger, Euclid on this ridiculously slow machine is in fact 10 times faster. So it's crossed over in the meantime. So at some point, when the data gets big enough, a smart algorithm is clearly smarter. So in some sense, what we're saying here then is you can have the biggest cannon on the block, the most firepower that you can imagine. But being smarter is often smarter than using more firepower. So the algorithm is absolutely crucial. If you really want a program that performs, you've got to be smart. You don't go for hardware. That's why software people, particularly C people, really rubbish hardware people. It doesn't matter what hardware you've got a smart enough algorithm, it'll perform. You've just got to make the algorithm smarter, and you'll get a lot more bang for your effort than mucking around with hardware. In the end, the hardware doesn't make that much difference. Now, how do I get back here? Okay, so, yes, we've seen all that. Okay, that's this fictitious 1 Hertz machine and this 2.1 billion instructions per second machine. Let's look at Wagner in computer science. And I tried it for some big Y's. So again, these are the number on the left here is my randomly chosen X. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 18 digits. You can all see that, I hope. And I've got my number on the right here, which is my smaller number, ranging from 10 to the 9 to 10 to the 17. And I've got here the performance times for Euclid and for exhaustion. And exhaustion is the right word. You see, 0.02 is constant. Really makes no difference what you give Euclid. As barbaric and primitive as that guy was, geez, fast. Exhaustion, maybe you could say the student way of doing it, is, well, if you gave it big enough numbers, 31 years you'll be waiting for it to come back to you. That's on a very fast machine. Okay, and this is by no means the worst case. So we try to understand now, okay, so doing it exhaustively, going up to the smallest of the two numbers in a loop, looking for a number which divides both. You can just think about loop, 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 every time, 2 divisions. I have to get my X divided by this number that I'm incrementing. So I start with 1, or sorry, start with 2. Does 2 divide into X? Does 2 divide into Y? No, that's 3 divided into x. That's 3 divided into y. No, 4, 5. Okay, you keep on going. So we've got 31 years for that case there, and well, obviously I did that by extrapolation. Well, now we get into what this course is about. What determined the performance? Can we generalize the performance? That's fine for those two numbers, but what's happening in general? What is the complexity, or what class of problems and solutions do these fall into? Exhaustion and the recursive Euclid. In the test case, how many modulus operations does the exhaustion algorithm do, for example? So we're now looking at the number of operations. The GCD is 1. Well, it's rather irrelevant. You see all of them there, GCD 1. So every number, you can see on the right there, the y is always a multiple of 10, and the left there has got a horrible number with 1, 2, 3 at the end, or 3, 2, 1. So there's no common factors, so it's got to go through, the point of that is, it's got to go through the smaller of the two numbers, the y iterations. Because there is no GCD, effectively. There's 1. They're mutually prime. So you can't stop halfway and say, oh, the half of the number on the left is enough, and you have to go halfway, and then I found it. Okay, so it's the size of the smallest number will determine the number of operations, and you've got to do 2. So it's 2 times 10 to the 17 in the last case. That's a big number. That's the number of division operations it has to do to check whether a particular number is a factor. In the last test case, how many in Euclid's algorithm, how many does it have to do? Well, you can't see that, but if you do it, in fact, 25. The number on the left is 87654321097857221 again, and on the right we've got all those zeros. Now, what do? Y to x, and on the new y is x divided by y remainder. So y to x, and we take the remainder of 8, 7, etc. with 1 as mod the 1, all those zeros, and we get that number there, 765, etc. So the 8 drops off. And we do it again, y to x, put the remainder. Y to x, remainder. Y to x, remainder. Y to x, remainder. And eventually we get 0, which means the GCD is 1. Okay, so number of operations, well, 25 divisions. Could we make, well, we could make it faster by using a loop. In fact, this is recursion. Recursion is heavy stuff for a computer. There's a lot of homework, housework I should call it, housekeeping got to be done to record the function stack, the stack corresponding to that function call, and you've got to repeat it again, so you have to copy the stack entirely on the function, all the data again, every time you do a recursion. Oh, 25 is nothing. It does that in milliseconds, microseconds even. So really, the fact you've done it recursion, which is the slowest way of implementing anything generally, you could have made it even faster if you used a loop and just done 25 iterations on the loop, moving the y to the x and putting the remainder in the new y. So, in fact, most of that 0.02 is housekeeping. It's not even the program. It's just the machine taking time to do the recursion. So, okay, there are the two analyses of the last case. What about in general? Well, now it starts to get a bit more complex. Okay, let's look at the exhaustion. Any one of you should say, this is dumb. Not because it's exhaustive. We think there's a good reason to use exhaustion. But for the first, just think about it, what you're actually doing here. Am I going too fast here now? We only have to go as far as the smallest. We all know that. That's why we're at this course. We know that. We can assume that. We can, where am I? Look at the loop and exhaustive again. This loop does 2 y operations, where y is the smallest of the pair. We know that. The loop of the early, we can actually say that instead of calculating every GCD till we get the greatest GCD, why don't we start at the top and get the first GCD, which is the greatest? Go the other way around. Why didn't I think of that in the first instance? Write the program to start from the top and go down. What top do we pick? Not X. We pick the smallest of X and Y. Why? And we go down. The first number we come across, we're finished. We don't have to find all the other CDs, the common denominators. We have to find just the first one, which is going to be the greatest because we're starting from the top. It's an obvious thing to do. So, and exit early. So there's our very sophisticated little program, which is exactly the same, except the increment smallest decrements to with I minus minus, that's an I equals I minus 1 in C, if you didn't know, and it goes down to I equal to 1, less than or equal, or greater or equal to 1, as long as I is greater or equal to 1, it's going through the loop, and it's got this extra condition on the loop, which tells us to bomb out when it's finished. Okay, so we're going down and we're exiting early. Okay, very simple. It's a real optimization. You would think it's an optimization, but optimizations can bite you in the bum. Optimizations aren't necessarily good things. Why am I not seeing that? Okay. Okay, so that's the early version of exhaustion.